The answer is yes. We can use Newton's method. As we mentioned before, Newton's method is one of the derivative-based methods. Newton's method is developed by applying the necessary conditions. Suppose we have a function f(x). The necessary conditions for the function f(x) to have an optimal is the first derivative is equal to 0. We use f prime to denote the first derivative. If we want to find an optimal of the function f(x), we need to solve this equation and find the roots. We can use Newton's method to solve this equation and obtain the roots. How does Newton's method work? Let's look at this graph. In this graph, we have the curve of function f prime x, which is the first derivative of the function f(x). In this graph, x star is the root of the equation f prime x is equal to 0, which we want to find using Newton's method. The key idea of Newton's method is to start with an initial point. This initial point is close to the true root. At this initial point, we can draw a tangent line of the function f prime x. At this point, the function f prime x is approximated by this tangent line. Then, using this tangent line, we can get the intercept of this tangent line on x-axis, which is called x-intercept. In Newton's method, this x-intercept is considered as a better approximation to the root of the equation f prime x is equal to 0. If this process is iterated and we keep find better approximation to the root, then finally we can obtain the root of the equation f prime x is equal to 0. Based on this, we can derive this formula to calculate a better approximation to the root for the next iteration based on the current approximation to the root. How can we derive this formula? Let's assume the current approximation to the root is xk. Then the function value at this xk is equal to f prime xk. As we mentioned, at this point, we will use the tangent line to approximate the function f prime x. The slope of this tangent line at this point xk is equal to the first derivative of f prime x, which is also the second derivative of the function f(x) at xk. And also this tangent line passes through this point xk and f prime xk. Based on this, we can write the tangent line equation, that is y minus f prime xk is equal to f 2 prime xk, the slope at xk times x minus xk, right? Based on this tangent line equation, we can obtain x-intercept, that is y is equal to 0. Then we can get minus f prime xk is equal to f 2 prime xk times x minus xk. Then we can get x is equal to xk minus f prime xk divided by f2 prime xk. This x is a better approximation to the root at next iteration, the iteration k plus 1. Then this one is xk plus 1. Then we obtain this formula. In Newton's method, better approximations to the root can be found using this formula until the difference between two successive better approximations satisfy the specified tolerance. Then the root for the equation f prime x is equal to 0 is found. As we discussed before, a saddle point also satisfies this equation. That means Newton's method may find a saddle point which is not an optimal for the function fx. In other words, Newton's method may not always find an optimal for the function fx. Let's see what Newton's method implies about the function fx. Suppose the function fx is approximated by a quadratic function at xk. We can develop this approximation by using Taylor's expansion. That is, fx is equal to fxk plus the first derivative of fx at xk times x minus xk plus 0.5 times the second derivative of fx at xk times x minus xk. Well, I think you have learned this Taylor's expansion from your previous mathematical courses. If we want to find an optimal for this approximated function, we just obtain the first derivative and let the first derivative be equal to 0, then we can get this one. From this equation, we can get x is equal to xk minus the first derivative of fx at xk divided by the second derivative of fx at xk. If we let this x to be the approximation at the iteration xk plus 1, then we can get the exact same formula that we have discussed. This means Newton's method is equivalent to using a quadratic function to approximate the original function fx and applying the necessary conditions to this quadratic function. To find an optimal, let's use Newton's method to find the optimal solution of the function fx is equal to x squared minus x. First, we need to provide an initial point. The initial point x is equal to 3. Then, at this point, we need to calculate the first derivative of the function fx and also the second derivative of this function fx, which is equal to 5 and 2 respectively. Then we use the formula to find a point for the next iteration based on the current point. Then we find the point x1, which is equal to 0.5. From x1, we can also use that formula to find x2, which is also equal to 0.5. Then we can see the difference between x1 and x2, the difference is equal to 0. That means we find the root for the equation f prime x is equal to 0, right? Then we will see the minimum is at x is equal to 0.5. From this, we can see we find the minimum in one iteration. This is because this function fx is quadratic. If the function is not quadratic, then we may need additional iterations to find the minimum. Let's look at this example. In this example, we want to find the minimum of the function fx is equal to the fourth order of x minus x plus 1. This function is not a quadratic function. We also specify the tolerance, which is this number, 10 minus 7. We start from an initial point. Let's assume we start from x is equal to 3. At x is equal to 3, we need to evaluate the value of the first derivative and also the value of the second derivative, and use the formula to calculate a point. For the next iteration, we calculate the point x1, which is equal to this number. Then we can compare the difference between x1 and x0, which is equal to 0.991741. This difference is larger than the specified tolerance. That means we need to continue. We continue to evaluate the first derivative at x1 and also the second derivative at x1 and use the formula to calculate the point for the next iteration. We get x2. x2 is equal to 1.36015, this number. We also need to compare x1 and x2 and calculate the difference between x1 and x2, which is equal to 0.649109. This difference is still larger than the specified tolerance. We need to continue. We continue. We do several iterations, and we get different value for x, and the difference between the points at two successive iterations. From this table, we can see the x value at iteration 7 and iteration 8. They are very close. The difference is this one, which is less than or equal to the specified tolerance. Then we can stop here and we find the optimal solution for the function fx. Now we can summarize Newton's method. As we discussed, Newton's method actually approximates the original function fx by a quadratic function. If the original function is a quadratic function, then we can find the optimal in one iteration. In Newton's method, we need to calculate the first derivative. We also need to calculate the second derivative. The second derivative is in the denominator. If the second derivative is close to 0, then Newton's method will converge very slowly. If at some point the second derivative is equal to 0, then Newton's method will fail, because we cannot use that formula to find the point for the next iteration. And also, in the Newton's method, we need to provide initial point. If the initial point is not close enough to the minimum, then Newton's method will not converge. Now we introduce another derivative-based method, the secant method. This method is also used to solve the equation f prime x is equal to 0 from the necessary conditions applied to a function fx and find the root for this equation. As Newton's method has been developed, why this method is also developed? This is because Newton's method requires to calculate the second-order derivative of the function fx. At some point of the function fx, the second derivative may not exist or may be equal to 0. In both situations, Newton's method will fail, will not converge, and also the calculation of the second derivative is often more time-consuming than the calculation of the first derivative. To avoid the calculation of the second derivative, the secant method approximates the first derivative of the function fx by a straight line using 2 points. At these 2 points, the first derivative have opposite signs. Then the secant method uses the slope of this straight line to approximate the second-order derivative. This is the key idea of the secant method. Let's look at this figure. In this figure, the first derivative of a function fx is described using this curve. We want to find the root of the equation f prime x is equal to 0, that is x star, in this figure. We take any 2 points P and Q on the curve and make sure the first derivatives at these 2 points P and Q have opposite signs. Then the first derivative can be approximated by using this straight line, which connects the point P and the point Q. Based on this, it is not difficult to write the equation of this straight line, which should be f prime x minus f prime xq is equal to m times x minus xq. Here, m is the slope of this straight line. Based on these 2 points P and Q, we can calculate the slope of this straight line. That will be m is equal to f prime x q minus f prime x p divided by xq minus xp, right? Using this straight line equation, we can find the intersection of this straight line with x-axis, that is x-intercept. We just let f prime x is equal to 0, so then we can get the x-intercept of this straight line. That will be negative f prime xq is equal to m times x minus xq. Then we can get x is equal to xq minus f prime xq divided by m. In this graph, we use the symbol x tilde p to denote the x-intercept. Then we have x tilde p is equal to xq minus f prime xq divided by m. In the secant method, this x tilde p is considered as an approximation to the root x star. Now, if we let this x tilde p as xk plus 1 and let xq is equal to xk, then we have xk plus 1 is equal to xk minus f prime xk divided by m. Then we can get this formula. This formula is very similar to the formula in Newton's method. The difference is this denominator. In Newton's method, the denominator is the second derivative of the function fx at xk. Here, the denominator is the slope of the straight line that is calculated based on the first derivative at these 2 points, xp and xq. In other words, the secant method imitates Newton's method, right? So this method is also called quasi-Newton's method. Using this formula, we can do iterations and find a sequence of better approximations to the root of equation f prime x is equal to 0. At each iteration, once we find a better approximation using this formula, we need to evaluate the first derivative at this approximation and check the absolute value of the first derivative at this approximation. If the absolute value is less than or equal to the specified tolerance, then we can stop and find the root for the equation f prime x is equal to 0, and also find an optimum of the original function fx. Otherwise, we need to use this approximation point x tilde p to replace xp or xq based on the sign of the first derivatives at these points, and make sure the first derivatives at the selected 2 points have opposite signs. In this figure, x tilde p and xq are selected. This is because the first derivatives at these 2 points have opposite signs. Then we have 2 new points for the next iteration. We keep doing iterations until the absolute value of the first derivative at some approximation point satisfies the specified tolerance. From the procedure of the secant method, we can see the secant method uses only first-order derivatives. That means the secant method can be used to find an optimal of the function fx in the situation where the second derivative of the function fx does not exist or is equal to 0 at some point. We use the secant method to find the minimum of the function fx is equal to the first power of x minus x plus 1, which has been solved by Newton's method. The tolerance is equal to 10 minus 7. We first choose 2 initial values for xp and xq both are equal to 3. Then we evaluated the first order derivatives at these two values. Then we can get negative 109 and 107. The first order derivatives at these two values have opposite signs, so these two values are accepted. If the signs are not opposite, then we need to try other values for xp and xq until the first order derivatives at these two values have opposite signs. Then we use the formula x tilde p is equal to xq minus f prime xq divided by m to calculate x tilde p, which is equal to negative 3. Then we evaluate the first order derivative at this x tilde p. Then we get this number, negative 109. This number is negative. We also know the first order derivatives at xq and also xp. We can see the first order derivatives at xq and x tilde p have opposite signs. Then we select xq and x tilde p as the 2 points for the next iteration. We do iterations. The values of xq and x tilde p and the first order derivatives at x tilde p in all iterations are given in this table. From this table, we can see we require 165 iterations to find the minimum. This minimum is the same as that obtained using Newton's method. However, Newton's method only requires 8 iterations. So we can conclude Newton's method performs much faster than the secant method. This is because Newton's method also uses the information of the second derivative of the function fx